Welcome back everyone. In the last lecture, we have seen how to design a controller using CASD tools. We took two problems in the previous two lectures. One was the quadrotor example that we took, and we had designed a controller in that case by introducing a 0 and then adjusting the gain. Similarly, for the next problem that we were tackling, where we had two objectives, overshoot and settling time, we had introduced two zeros in the controller and a pole at the origin, and then adjusted the gain to get to the controller that we want to reach the desired objectives. Today we start from that point and we will see that whatever we had done in the previous two examples leads to a kind of controller called the PID controllers. Let us dive deep into that now. This was the problem we had for the quadrotor. Now, here we had this controller. You can open up this controller into these two parallel blocks, and why can we do that? Notice that if you have a controller block which is say G1 plus G2 and your input is say US to it and the output is YS, then what can we write about the output? The output can be written as YS equal to G1S plus G2S whole into US, and this can be written down as G1S US plus G2S US. So, in other words, I can redraw this block into these two parallel blocks, which is say G1S and G2S in parallel, where they are taking input as US. US is the input to these two parallel blocks, and then the output can be summed up this way, and this becomes your YS. The same thing we can do here. I can open up this bracket and write it down as 9.052S plus 9.052 multiplied by 17.8571. Here this part I can consider as G1 and this part I can consider as G2, and in that way I can redraw the circuit, redraw the block diagram in this way. Notice another thing, 9.052S is one block which can again be redrawn as 9.052 cascaded with another block S. So, the output here also remains the same. If you give a US output here, YS being the output here, or Y1S being the output here, and US is the input here and Y1S will be the output here as well. Now, why are we doing this? We are doing this because this gives us some intuition or some more facts about the controller that we are using. Let us look at that from the time domain perspective. Here the reference signal will be in the time domain RT. The feedback, since we are taking unity negative feedback, here the feedback will be the YT signal itself, and here we will have ET. And in the Laplace domain, this is ES and this is YS. Now, notice what will be the output at this point. The output at this point would be 9.052 S into ES. This in the time domain becomes 9.052 ddt of ET, because if you remember, if Laplace transform of f of t is equal to f of s, then Laplace transform of ddt of f of t is equal to s into fs. So, the output at this point is proportional to the derivative of the error signal and the proportionality constant being 9.052. whereas the output at this point is 161.642 ET, which means the output at this point is proportional to the error signal directly, and the proportionality constant is 161.42. Hence, this part of the controller is called a derivative controller. So, this is a derivative controller because the output of this controller is proportional to the rate of change of the error, and this part of the controller is called a proportional controller because the output at this part is proportional to the error signal. So, as a whole, this entire setup becomes a proportional derivative controller or a PD controller. So, the controller that we had designed for the quadrotor example was a PD controller. So, in general, although this was an example, in general we can write down a PD controller in this form, where the output of this PD controller is given by Kp plus Kd ddt of Et, and Kp here is the proportional controller's constant, and Kd is the derivative controller's gain. Gain and constant, these are the same words, we will use it interchangeably. So, notice one more thing, what is the controller block that you have added here? If you remember, if you can look at this, you will see that the controller block here is nothing but S of Kd plus Kp, and this is nothing but, if you take Kd common, then it becomes S plus Kp by Kd. So, which means the controller that you have added here has a 0 at minus Kp by Kd, and the constant, the gain that you have is Kd. So, in other words, when from a root locus perspective, when you are adding a PD controller, it is equivalent to adding a 0 at minus Kp by Kd and adjusting the gain Kd. So, in our example that we had taken, in this example you will see that what will be our Kp value. So, our Kd value, here you can see our Kd value will come out to be 9.052, and where did we place our 0 here? This is minus Kp by Kd, which is the 0 position, which is minus 17.8571, and from here you will find that Kp will exactly come out to be 161.642. So, designing a PD controller is equivalent to introducing a 0 on the root locus and then adjusting the gain such that you reach to your desired pole location. Okay, I mean, we have done this. So, in the case of the quadrotor, the controller that we designed, although we never named it, now I am naming it. The controller that we had designed was a PD controller because it has a proportional part and a derivative part. Okay. So, PD controller is equivalent to adding a 0 and adjusting gain on the root locus of the open loop transfer function. Suppose you want to design a PD controller. So, of course, there will be a question, when do I have to design a PD controller? Okay, all those questions also will get answered, but what is the effect, what is the use of this, each of these controller, proportional, derivative, what is the use of this? We will discuss that in today's lecture, but let me first explain it from the root locus point of view. So, from the root locus point of view, when you are designing a PD controller, it is just that means the controller that you are designing will have a 0 and will have the gain parameter. These two parameters you have to change so that you reach to your desired pole location, or that means the root locus passes through the desired pole location. We have done an example like that. So, you know what is the meaning of designing a PD controller now from a root locus point of view. So, if we have a PD controller, we will have a P controller also as well, right. If you do not have the D part in it, then it becomes a P controller. Okay. So, you can see that in a P controller, you will have a block like this, where the output will be just Kp into Et. the output of the controller is just proportional to the error signal that is getting as input to the controller. Now, from a root locus point of view, what is the meaning of that? That is basically the root locus. In root locus, when you are changing the k value, remember there was a k value which you are changing from 0 to infinity. That k value when you are changing, that is nothing but your designing of a P controller. So, if you change the k value such that your root locus, you are at the point on the root locus which is the desired pole location, and you find out the k value at that point, that is the value of your Kp. Okay. So, we talked about PD controller, we talked about P controller. Remember the other example that we took, this was the other example in which we were trying to find out the value of k for 40% overshoot and 2 second settling time, and we found that we were not able to design this using a simple k. So, what is the meaning of using a simple k? What was the block diagram like? The block diagram was something like this, right. This is the block diagram. So, you can see in this block diagram what were we trying? We were trying to find out a k. So, what is this controller? This is a P controller, right, because here input is error signal, output is just proportional of that error signal. So, this is a P controller. So, we found that with a P controller we were not able to solve the problem, right, and therefore, if you remember, we went to the CSD app and then we introduced 2 zeros in the app, right, and a pole at the origin, and finally, we adjusted the gain such that we reached to a controller of this form, and this controller was able to achieve the overshoot and settling time that we wanted. Now, let us look at this controller and also try to break it down. If you multiply this controller, if you multiply the numerator here, you will get this, and then if you divide by s all the 3 terms on the numerator, so you will get something like this. Now, notice that this is again in plus term. So, this plus this plus this. So, this can be one block, this can be another block, this can be another block, all are in parallel to each other, okay, and this is what it is. So, the same thing I am drawing again, you see, this is how it will look like now. Now, this is what is Kp, right, this is the proportional controller, because you see the input here is the error signal. Okay, this is the proportional controller, this is the derivative controller. So, this is Kd, we are calling it Kd. Now, you see we have a new thing introduced here. Okay. Now, what is this? Again, you see what are we doing? We have an error signal here, okay, which gets multiplied with 279.037, and then we have 1 by s. Now, what is the meaning of 1 by s? You see, okay, let me write it down in Laplace domain. So, basically we are doing this, right, Es by s, this is what we are doing. Now, if you take a Laplace inverse of this, what will you get? You will get 279.037 Es by s, that is nothing but 0 to t e of t dt. This is what Laplace inverse will look like. So, that means this part is acting like an integrator. So, this is an integrator, right, 1 by s is an integrator, s is a differentiator. So, 1 by s is acting as an integrator here, 1 by s is integrating et, and that is the output here. So, the output in this case is an integration of the error signal multiplied by this constant value. So, therefore, this is called a integral controller. So, we have proportional, which is the P part, we have integral, which is I, and derivative, which is d, and this is why we call such a controller as a PID controller. Okay, and you can see that this will be the PID controller structure, and what will be the output of the PID controller? Kp into E, Kd ddt of Et, then Ki integration of the error signal, that is the PID controller. So, if you have to design a PID controller, that is from the root locus perspective, it is equivalent to so designing a controller which has 2 zeros, 1 pole at the origin, and then you have to adjust the gain such that you reach to the desired pole location. So, now you have 3 parameters to play around with, which is 2 zeros and 1 the gain parameter. For this example, what is the output in this case? The output of the controller would be u of s is equal to Kp plus Kds plus Ki by S into Es, which is nothing but Kds square plus Kps plus Ki by S whole into Es. Now, this you can take Kd out from here, you will have S square Kp by Kd S plus Ki by Kd by S Es. So, then the gain that you will get will be your Kd, then you multiply this part out. So, this is your Kd, you multiply this part out, from there you will get the coefficients of S and the constant values, that will be Kp by Kd and Ki by Kd. Since you know the value of Kd to be 3.5265, you can easily find out the value of Kp and Ki as well. Okay. So, you can see what a PID controller is. So, now from the PID controller you can take off the D part, then it becomes a PI controller. Okay. So, if there is no D, then it becomes a PI controller. So, what is a PI controller from a root locus point of view then? So, what is the output of a PI controller? So, if you look at this block diagram, what is the output? So, if this is ES, so the output here is nothing but US will be equal to Kp plus Ki by S whole into Es. So, this is equivalent to S of Kp plus Ki by S whole into Es, right, and this can also be written down as, if I take out Kp, Kp S plus Ki by Kp by S into Es. Now, notice this is the controller, right, this is the controller. So, PI controller is nothing but introduction of a 0 and a pole, a 0 at the point minus Ki by Kp, a pole at the origin and then adjusting the gain K. Okay. So, this is what a PI controller is all about. So, there are different types of controllers that we can design. Okay. Till now, when we were doing root locus design, I have never named what controller we are designing. We are just going through our basic intuition. Okay, I want the root locus to pass through the desired location. Should I add a 0? Should I add a pole? All these things we did in the last few lectures. Now, I am actually giving these things names. Let me now try to focus on when to use which controller. So, what happens is, suppose you have a system, you have a system already with you. One way is that you found out the transfer function of the system and then you had some specifications, use the transfer function, the tools that we have talked about, root locus and all that, and then you go ahead and try to get to the controller that you wanted to design. Now, there can be cases where this might not even be required. You do not want to get into the specifications also, say. Suppose you have an example where you have a DC motor where you want to control the speed of the motor. You do not care much about what is the specifications and all. Okay. Then you do not even have to go into all these ideas of finding out the transfer functions and all. Directly also you can go for PID controllers. Okay. Now, question is when to use which type of controller and what is the meaning of directly you can go for the PID controllers. Okay. So, let us try to understand that, and for that we will look at each of the controllers P, I and D part separately and try to understand what is the effect of each of these part on the output, on the response of the system. So, if you have a P controller, this is the basic diagram of a P controller, okay, and this is standard basic diagram of a P controller. Now, suppose you want a straightforward response, that is that the current error or the response here should directly be influenced by the current error. I mean, you do not want many things, you just want that the output should directly be influenced by the error that it has, and then you can directly go for a proportional controller, okay, because it will respond immediately to the changes in the error, because the output here is directly proportional to the error at that instant itself. So, the output here will directly get influenced at that particular instant itself. Now, the problem with these type of controllers is that it might have steady state error, okay. We have seen that. Remember the example of 1 by s plus 2 into s plus 4, that was the example that we took where we had two specifications, 40% and 2 second one. In that example, you saw that although we reached to our desired locations or desired objectives, we still had steady state error, and the reason for that we figured out that because the type of the system was 0 to start off with, and so for a type 0 system unit step input there will be steady state error, and that is what we were seeing. So, with the P controller we were not able to solve that problem, right. So, in that case we will have to go for something else. Okay. So, P controller, if you need quick reaction to your current error, then you can directly go for P controller. Okay. Most of the cases P controller although it looks like P controller will help, but in most of the cases some amount of D and I is generally required. So, let us see what an I controller does. So, what is an I controller? Now, look at the I controller. Okay. So, see, in the I controller there is an integral action is added when you need to eliminate the steady state error. So, what is an I controller? An I controller, only I, no P, no D, only I is Ki by S, right. So, if it is a Ki by S, if you look at the open loop transfer function now, so before the controller was added, the open loop transfer function was this. After the controller is added, the open loop transfer function becomes this, right. So, you see what we have done in this process, we have increased the type of the system. So, if this was a type 1 system, now we have made it a type 2 system. Say. If it was a type 0 system, then we have made it into a type 1 system now. So, when you increase the type of the system, we know that the steady state error also decreases, right. So, for step input type 0 system, steady state error will exist, but when we increase the type of the system, then the steady state error becomes 0 for step input. However, for ramp input there will be steady state error. So, for a type 1 system, if I introduce a I controller, it becomes a type 2 system. In that case, steady state error due to ramp input will also be removed. Now, so of course, you have to decide what to do, because what is the meaning of steady state error will be going out? You have to first decide how do we plan. You first decide what is the reference trajectory, right. Why? Because what are you trying to get to? If you are trying to get to a particular point, so for example, for the DC motor, if I want to get to a particular speed, okay, a constant speed, then the step input will be a reference, because I want to get to say 50 rpm. For the quadrotor, say if the quadrotor has to move to a particular point, then I know that is the step input, because I am reaching to a particular point only. However, suppose the quadrotor has to follow another device which is increasing its speed, say. Okay. So, in that case what will happen? In that case, uniformly, suppose it is increasing its speed uniformly, then you are no longer your reference is a constant value. The reference is also increasing uniformly, right, with time. So, in that case your type of the system has to be more than. So, in that case, maybe even if it is a type 1 system, it might not help. In that case, your reference signal becomes a ramp signal maybe. So, if your reference signal is a ramp signal, then you have to go for a type 2 system for the steady state error to be 0. In that case, even if you type 1 or a type 0 open loop transfer function, you have to add a I controller so that you can increase the type of the system. Okay. This is from the perspective of type. Okay. Now, can we get more intuition about the integral controller? Let us look at that. So, what is the integral controller actually doing? The output of the integral controller is integration of the error signal and then multiplied by some constant. Okay, let us forget about the constant for the time being. What is important is that it is an integration of the error signal, which means it is not just looking at the error signal at that particular time instant, it is looking at the error signal from the previous time also, from 0 till the present time, and then it is summing it over or integrating it, and then the action taken by the controller is on that quantity, not on the error signal at that particular instant. For the proportional controller, remember what was Kp doing? Kp was just multiplying with E, and the output was exactly at that instant only. Whatever error was there, it was just multiplying that and giving you the output. In this case, the integral controller is taking into account all the accumulated error also, because it is integration from 0 to t. So, it is taking into account everything and then it is deciding. Okay, let us go back to the proportional controller once. Look at the proportional controller. Okay, so if in this proportional controller, suppose, okay, let me say that this is 1. Okay, suppose my output, I have reached the output, I have reached the reference signal. So, that means my output will become equal to the reference signal. If my output becomes equal to the reference signal, what is my error signal? Error signal becomes 0. But if error signal is 0, we know that what will be the output in this case? 0. So, are we giving 0 input to the plant? Because if you give 0 input to the plant, what will happen? Output will be 0. Then again the error will increase. How does it help? It does not help, right? So, that is the reason, and integrator is very important, and that is the reason actually for type 0 system there is always a steady state error. So, in case of integrator, what is happening? Integrator, this quantity is not 0 when E is 0. Suppose at a particular instant Y and R became equal, H is 1 for example. In that instant E becomes 0, but does it mean that the output of the controller becomes 0? No. You see, the controller output depends not only on that particular instant, it is also depending on the previous instant. So, it is taking care of, it is also considering the previous instance. So, the output does not become 0 in this case, and that is how actually the steady state error is taken care of, because even when the error has become 0, we have something at the output of the controller which helps it to comes back to the reference trajectory. Okay. Now comes the question. So, does it mean that this controller does not help us anywhere? It helps us, P controller, because you see, suppose it was a type 1 system from steady state error point of view. Suppose this was a type 1 system. So, if it was a type 1 system, I know that it would be something like this, numerator by S times of ds. Now, what I can do is, theoretically I know that this S I can take and put it here, right. So, it is almost equivalent to an integral controller again. The proportional controller is almost equivalent to an integral controller when the type of the system is higher than 0, because I can take that S and bring it here. Then again, what is the output here? Then the output here is integration of the error, right. So, that is how proportional controller also helps to get you to the desired set point. Okay. So, but if it is a type 0 system, it will not be able to get to the desired set point directly. Great. So, we know what an integral controller does. So, when do we have to use an integral controller? Whenever you see that there is a steady state error, we need to use an integral controller. From the type perspective, we are increasing the type of the system, that will also bring down the steady state error, right. And you also understood how the steady state error is brought down, because it is taking into account the accumulation of the error from 0 to t. So, there should have been a dt here. Okay. So, whenever your process must settle at an exact reference point, okay, then the I term is essential. This is when we have to use I. So, now you see, we are not even talking about any particular overshoot or settling time or anything. I have just talked about from an intuition point of view. You look at your system, or you can see that the system is not getting to the desired reference trajectory. So, I need some integral action so that it goes to the particular trajectory. Okay. We will see some demo examples also, then you will understand what I mean by that. So, we do not even need transfer functions in these type of scenarios. So, one problem is that, first of all, there is a tendency that if you increase the type of the system, the closed loop transfer function might become unstable, because when you are increasing the type of the system, open loop transfer function, you are introducing a pole at the origin, right. If you are introducing a pole at the origin, remember, what does pole do? Pole try to repel the root locus. If the root locus gets repelled, root locus branches gets repelled in such a way that it goes to the right half of the complex plane, then we have an issue, right. So, in general what happens, I mean, if the type of a system increases, there is a chance that you might end up with oscillations also, okay. So, there is a trade off, you cannot just keep on increasing the type of a system, somewhere down the line there it might lead to issues, okay. And then the other issue is what is known as integral wind up, which we are also going to discuss in one of the lectures later, okay. This is a practical problem that integrators have. Finally, we have the derivative controller. Now, what is the derivative controller? The output in this case is ddt of Et. So, it is finding of the slope of Et, right. Ddt means what? Slope, right. It is finding of the slope of Et, and then it is taking action on that. Okay. So, in that way, think about it. So, suppose this is the error signal, this is the error signal. So, it is fluctuating quite a bit, right. So, what will happen is, what is the idea of the derivative controller? The derivative controller takes action on the rate at which the error signal changes. Now, if the derivative controller is taking action on the rate at which the error signal changes, it tries to bring down the rate maybe. So, what it is trying to attack the oscillations of the output. So, in that way you see derivative actions is especially helpful if you need to reduce overshoot or to respond to rapid changes before they become too large. So, integral controller was taking care of the steady state error, it was bringing down the steady state error. So, whenever you need to bring out the steady state error, you go for integral controller. Okay. So, this integral controller is acting on the steady state part of the response. Remember, the response was divided into transient and the steady state part. So, the integral controller is acting on the steady state part of the response. Derivative controller on the other hand is looking at the rate of the error signal, right, and it is trying to bring down that, reduce that. And when do we have oscillations on the error signal? When your output yt will have oscillations, right, and when does the output, the response have oscillations? It is on the transient phase of the response, right. In the transient phase there will be lot of oscillations. So, during that phase the derivative controller is acting. So, the derivative controller tries to bring down the overshoots during the transient phase of the response. So, the derivative controller acts on the transient part, or it tries to reduce the overshoots, whereas the integral controller tries to reduce the steady state error. So, you look at the response of your system. Suppose you designed a system just using a proportional controller. Okay, proportional controller is instantaneous. You designed a system using a proportional controller. Look at the response. If the response is such that lot of oscillations are going on there, you go for D controller. You go for PD controller. Okay. If you see that even with PD controller the oscillations have come down, but there is a steady state error, go for PID controller, use the I. The oscillations are not that big, you are fine with it, then do not go for a D controller, but there is a steady state error, then go for a PI controller. If you have a steady state error, go for a PI controller then. So, this is how you decide, and this is quite an intuitive thing. Designing PID controller is very intuitive in that sense. Have I talked about transfer functions anywhere during this discussion? No, I have not gone into transfer functions. If you have to do it analytically using mathematics and using the tools that we have used, you should get the transfer function, and then also you can design these PID controllers. Exactly by the procedure that we did in the last 2 lectures. That is what PID controller was. Okay. But if you do not have these specifications, you can directly go by intuition also. You do not have to go through all this. Instead of that, take the system and then run it with a proportional controller, look at the response, and based on that you can tune your controllers. The word is tune. Tune means you can find out the value of Kp, Ki, Kd, okay, and use that to get to the desired objective. So, the features of D controller are, it reacts how fast the error signal is changing, it helps reduce overshoot and can improve damping. Now, this is very sensitive to noise, we will talk about this, and we will also have to use filtering for that. We will talk about this in the subsequent lectures, okay, last 2 points. But those are practical issues that we face during implementation of PD controllers, okay. So, the takeaway is that, okay, if you have a control system architecture of this form, okay, what we are doing here is, our objective was to design this controller CS, right. So, how did we design this controller CS? We came up with different methods, okay, using the root locus method we came up with that, and also through intuitions also you can go and design controllers. Now, you see here the output is fed back into the system, and then we are designing the controller. The input to the controller is the error signal from the reference and the output of the feedback transfer function here, and hence these type of controllers, since it depends on the output directly, are called output feedback controllers. And in output feedback controllers we have gone through P controller, we designed a PD controller, we designed a PID controller, and you can also have examples where you have to design a PI controller. So, you can have combinations of P, PI, PD, but P will generally be there, P will always be there. You do not have an ID controller as such, okay. P is always there because that is required. Your proportional controller will always be there. So, either go for P or for PI or for PD or for PID. Implementation also becomes easier, okay. Now, there are other output feedback controllers also, lag controller, lead controller and lag lead controller. Since we did not go into design perspective related from the perspective of frequency response, see whatever we have designed, we already always looked at the time response, we took the performance criteria from the time response as percentage overshoot, settling time, these were all related to the time response of the system. Okay. We have not gone into the frequency response of the system, that is from the Bode plot. There also we have some specifications that can come up, like for example phase margin, gain margin, these are words I am telling you because I have not gone through these things, and I do not think I will be going through these things in this course, because there are a lot of things to cover. We have to go to the modern control theory part also. So, in this course, as promised, I am not going into the frequency specifications part, which is the gain margin, phase margin, all these things. There is something called Nyquist plot. If you want, you can read this part up on your own, okay, or you can also go through other NPTEL courses on control system, which will have details about these part. However, for us, we are just concentrating on these 4 controllers and we will be using that. Now, in the next lecture, what we are going to do is, we are going to find out ways to tune these values Kp, Ki, Kd. We already know how to find out the value of Kp, Ki, Kd using CSD tools, but even if you do not know the transfer function, you can come up with a value of Kp, Ki, Kd, and that is what we are going to do in the next lecture. Thank you.